Okay, now going back to the theoretical guarantees for the Dagger algorithm, for the Dagger approach. So the Dagger approach is proven to be what's called a no-regret algorithm, a no-regret training approach. What does that mean? So first of all, it will converge on the optimal policy. We didn't define an optimal policy. In this case would be the policy that is most closely imitates the demonstrator, right? It cannot do that perfectly, again, if we assume some limitation in our approximation policy, which is usually the case. But this is a stronger result than just convergence. It tells you that not only will you converge, but you'll converge quickly. What does it mean? So let's define no-regret algorithm. So in online learning provides us with a policy that evolves over time, right? In every iteration we have a policy and it gets hopefully better and better, converges to some optimal policy. Applying the policy at every time step results in some loss. It can be looked at as negative of the reward in reinforcement learning, but in imitation learning there's a specific loss function. And let's say that the loss, the accumulated loss at iteration I, is Li of pi I, okay, at this iteration. As we saw before, the loss gradient is used to train the next policy, which, when applied, incurs the next loss, right? Each iteration has its own loss. What is the regret? The regret is the sum of differences between the loss incurred at each iteration and the loss that is incurred by our best policy. So again, this is not necessarily zero, right? Because, well, at convergence, this whole expression is zero, but this is not necessarily zero due to limitation in our approximation, right? Our best policy might not be able to reach a loss of zero. So regret is defined with respect to the best policy that we can achieve. And we sum the differences in regret between the observed, the loss in the observed policies, and the best loss that we can obtain if we just know the best policy under our assumptions. Okay, so this is known as regret. A no-regret algorithm is one that at the limit results in a regret that is zero. Okay, results in zero regret. Of course, at the beginning it will have some regret, but as we accumulate more and more and more iterations, the regrets will tend to be zero. This is not always the case. We know of infinite sums, series that sum to infinity, or to some value that is not zero, but as I said, a no-regret algorithm will mean that at the limit the regret sums to zero. Now, we won't go over the proof, but Dagger is proven to be a no-regret algorithm. In practice, what it means is that it converges relatively quickly, guaranteed, right? Again, I cannot guarantee quick convergence. I cannot even define quick convergence. I can define no regret. I mean, they did that. And we can prove that this is a no regret algorithm. Now, of course, there are some assumptions regarding convexity of the loss function and learning steps. So, under some reasonable assumptions, they show that the Dagger is no regret. And you're more than welcome to go read the paper and see these assumptions and the full proof. So let's see some results for Dagger, for applying Dagger on the same driving domain that we've seen before. You can see here the results for this type of training, where the y-axis is the average falls per step, so we want to minimize those as much as possible, falling from the road. And the x-axis is the number of training data, right? How much training data we have. We didn't discuss this algorithm in the middle, the SMILE algorithm, don't worry about that, but we did discuss Dagger and supervised learning and just behavioral cloning. And you can see, as expected, that as the number of training data grows, Dagger quickly converges on the optimal policy, while behavioral cloning does not. Actually, at some point, the error even increases, because at some point, more data won't even be useful, right? You have all of these, you have sufficient data for the state space distribution under your demonstrator, and you learn that state space distribution, but still, you have situations where you diverge from that distribution, and then you'll crash. So you can see how in this case the behavioral cloning did not work very well. By the way, I'm assuming they had a very specific demonstrator in this case, right? A very good demonstrator that drives mostly on the middle. Of course, they can improve. You can improve the results for behavioral cloning by having a demonstrator that is more diverse, that drives all over the track, and also gets to the edge and recovers from that. That would have improved the results of the supervised learning agent, but that's not what they try to show here. They try to show that if you just take a good driver as a demonstrator, one that stays mostly in the middle, behavioral cloning won't do a good job. And this is indeed what we see here.